Considering the fact that calculus has baffled young people, students, I just thought of starting with a new series of videos which would eventually help the students to build up the concepts of calculus. Welcome to this first episode, the first video on Introduction to Calculus, where I would be discussing on the initial concepts on which the areas of calculus, calculations, limit, integration, differentiation would be going ahead. So I hope that you would be watching this video. If you have any further suggestions or if you want me to make any further video on certain concepts of calculus, please do let me know. So I just mentioned this as an introduction to calculus, which we would start building on certain fundamental concepts. Well, just to start with of the introduction of calculus, what we need to know is that what is a function? There has been different types of definition of what is a function, but I would like to show you a function as something like this. Let us consider the function to be something like this kind of a magical box. Say for example, we draw a box something like this, right? And what we will consider here is that there is something which is considered to be an input. So here we are putting in some values which would be considered as an input, and here what we will get it as an output. So this is a kind of a box which gives us something on the input and something on the output. And let us consider what we will deal inside the input as x5, right? So what is basically a function is that we would consider whatever is coming inside this box would be multiplied by 5 times, and it would be giving the output. So this is basically a simple box which has got an input and it has got an output. Considering the fact that, say for example, we first input a number which is 2. So what would be the output of the first number? It would be 2 times 5, so it would result into 10. Considering the fact that we again input another number, and this time what we input the number as 3. This box will process it and it would eventually give as 15. Again, say for example, we input another number, and this time what we do is that we input the number as 4. So what comes out of it is 20. So what we are doing essentially is that we have devised a kind of a box where whatever we are doing an input, it is multiplying it by that number with 5, and it is giving the output. This is typically an example of a function, right? So now what we can write this function, we can eventually write this as f times x equals to 5, right? So what we are doing over here, it is that we are considering f times x and we are giving it as a 5. I think this is now quite visible. I'm sorry that the focus was going out. So you see whatever is coming, 2 times 5 it's 10, 3 times 5 is 15, 4 times 5 is 20. So this is basically what we call is a function. It is a kind of a box. Whatever it is, it gets the input and it provides the output. So we can always call this function as fx equals to 5 times x, right? So whatever it is coming, it is giving at an output. So this part is what we called is the output. This is the output, and this is basically the input part. So whatever it is happening, it is taking this as an input. This is a simple definition of a function. I'm not going into details of function, etc. This is a basically very simple explanation. And the question arises, shall we always take x? Because generally we have seen in mathematics that we always consider x to be the function, but it is not necessarily so. What we can do is that we can also write, say for example, f times a equals to 5a. This can also be in place of x. we can also write g times x equals to 5x. This is also what we can write, right? But remember one thing which is quite noticeable in case of a function. In general, you will see whatever the variable that it is taking in, this a and this one would be the same. Similarly, this x and this x comes to be the same. Eventually, what happens is that we can simplify this function, and what we can write is something like this. We can write y equals to fx equals to 5x. This is generally written because why? Because we are using y instead of fx, as it is very easy to write. So in the same way, what we can do is that if we are inputting values over here for x equals to, say for example, I will write for x equals to 2, what we get is similarly the same. It will get 5 times 2 equals to 10. If we consider x equals to 4, it would be 5 times 4 equals to 20, and so on. Alright, so we are using y instead of fx because it is just simple, it is easy to write. Considering this, what we can also say, for example, we are taking a function, say, let me give you an example, ga equals to 2a squared. For example, this is another function. And we would like to know, say for example, what is g b plus 2? What is this value? What we can do is just substitute this value over here, and we get 2 times b plus 2 whole squared. Right? So this is the answer. So just to start initially, this is the function. Function, you can imagine it as a kind of a box where there is a variable called x, whatever the, or x times 5. Here we can eventually put anything like that, x times 5, x times 7, x plus 5, x multiplied, divided by whatever. This inputs will give you the output. F of x equals to 5x, this is general notation of a function. We have shown through substituting these values what is the effect, what are the results that if we produce. In general, the input and the output variables are the same. We can also use certain other notations in order to symbolize a function. Now we come back to calculus, that is what we have eventually learned, that say for example, for example, what we do is that we have a function, we call it y equals to fx. That's a simple function, and here we write d by dx, right? This is the general the way we do. And when we are writing d by dx or dy by dx, say for example, we write dy by dx, we can also use this particular I would say notation. Let us write it in this way. We can also write it as d by dx of y. Okay, so it is eventually the same. If you put y over here, this d by dx, it becomes same. It becomes dy by dx, right? So we can consider this part. We can consider this part as an operator. We consider this to be an operator, right? Right. dy dx, this is basically operator, and this is what we call is the derivative of x. So we call it as derivative of x. Similarly, in the way of integration, what we can write, we can use this elongated x, and we write it as fx dx, right? And we call this part as the operator. So instead of imagining dy by dx or the integration sign as something like a variable or something, let us consider, or let us think these to be an operator. These are the operators which are operating, and whatever be the functions, etc., that you will be watching over here, that would be beside this operator. We were soon looking into this part in much more details. So I just wanted to tell you that what is an operator. So okay, so let us consider this situation, and we write this one. again I will use this notation. We use dy by dx, and in this way what I can do is that I write it as d by dx, and I write y over here. There's a basically a intention of doing so. I will slowly reveal it in my video. So just like we have this one d by dx, y, this is basically the function. This is basically the function that we are working on. Similarly, we have an integral sign, and with this we have a function that is f times x, fx, okay, of a function. The function that we integrate gets stuck in between the two operators. So I will show you in a different color, and I will make it bold so that you can understand. So let us write this once more. Just a second. Yep. So we will write it in this way. Say for example, I use this symbol of integration, right? And I put over here, let me put a different color. This is fx dx, right? Now what is important over this part is that this is the symbol, right? So I can write this as a symbol, right? And this is also the symbol. This is also the symbol. I'm just trying to make you understand the notation. This one is the function. This one is the function, right? So this is the way in which it happens. Between these two functions, between these two symbols, whatever this one and this one, this function is getting stuck up. This is the usual way of writing the notation. So the function gets stuck up between the two symbols. Now differentiation is actually an inverse of integration. That means I can write it, say for example, let me put it in this way. If I write d by dx and I write y over here, is inverse of, I can put it this one, put it integration f of x dx, right? So you can imagine this one, this part as something like this. Say for example, if you have something like say for example root over x, right? And if I square this x, root over x is squared, ultimately it will give you the same x, right? So it is the same thing. That means whatever you are doing in differentiation, it is getting exactly the opposite. So you get essentially the same thing. Let me give you an example. If I want to do something like this, d by dx, I write is d by dx, and I integrate, differentiate and integrate f of x of dx, what would be the result? The result would be fx, right? So the basic idea of showing is that this part and this part, if it is going in this way, it is also coming in this direction. So differentiation is exactly the inverse of integration. Given the rules, they basically they are inverse of operation. In order to show that, I will cite a simple example. Say for example, if I get a value which is x to the power 4, and we want to find the antiderivative. I want to find the antiderivative. That means I'm trying to find the indefinite integral of x to the power 4. How will I do that? For example, so I make a summation and I integrate x to the power 4, right, of dx, and what I get simply is x to the power 5 whole divided by 5 plus the constant c, right? So this is something what you can imagine like this. Like we know the concept of radical and radicand, right? Say for example, if we have something like root over x. So root over this part is called the radical. And whatever gets in, say for example x, this is called the radicand. So this is a very familiar school days concept, radical and radicand. So this is how it happens. So the final what the result that we got of by doing an antiderivative, and we have seen this part also. So it is exactly the opposite. That means whatever the derivative values it is getting, it is exactly the inverse which is coming in doing an integration. Differentiation and integration, it yields the same result, but it acts as an inverse operation. So we have shown this. This is an example just to find out what is the antiderivative. So whatever it is going inside, this is the radical part and this is radicand. So, and this particular operation is called integration. This one, x4 dx x2, this is called integration. Sometimes it is also called evaluation, a different way. But the most common thing which we call is, this is called integration. This is called integration, or you can call it evaluation, etc. We pass over to the next part of my video where we will talk a little bit about notation. Now what do we mean by notation is something like English vocabulary, where we know the words in English, synonyms, antonyms, and it becomes easier for us to express the thought. Like if we do not have enough amount of vocabulary, we won't be able to reveal the thoughts. So vocabulary and mathematical notation are similar. We can express our thoughts in a better fashion. So I will just consider one graph. Let us consider this part. Okay, let us take a simple graph over here, right? And we get a function. We get it as fx. It is looking something like this. This is my function, so I mention it as fx, right? And we want to find the slope of this graph. Okay, what we want to do is that we want to find the slope of the graph. So what we do over here is that we know that the slope is slope equals to rise over run. So let me just write it for your convenience. Slope equals to rise over run. We know what is rise. This part, it is rising, and this part is the run. Okay. So now what we get is that, say for example, we want to find the slope of a value at a particular point, and I mentioned this point as x, right? So this point is x. So what we do over here is that we join this point up to here, right? And then we move this x to this point so that it becomes delta x, and we drop a further point and we join this axis. So we get this this displacement, or this value, which is we can call it as delta y, and this is the part which we are mentioning as the y-axis. Obviously this is the x-axis. So what we can do is that we can simply use the formula. So if it is slope equals to rise over run, so we can just put over here what is the rise, that is delta y, that is the change in delta y. What is the run, that is delta x, and we get the slope, right? So this is quite a good kind of an approximation. Now if we want to do it, make it further small so that we can get a kind of a further approximation, we can just make another graph so that I can show you that what is the, we are making a small change. See, for example, I will draw another graph for you, right? And we use the same function. We don't make any further changes. So we use this y equals to fx and we get something like this, right? So this is the same one. Yeah, this is the fx, right? And what I'm going to do is that if we are in the same axis and we get an x over here by dropping, I'm going to make a very little change, infinitesimal small change from here to here, this one. And we call this part, which is a very small change, instead of delta x, I call it as dx, right? So we get something over here, and it is so small, this part, which was a bigger y, we get something called dy, which is a very infinitesimal small change. So what is the slope over here? So the slope, we can denote it as m, will be dy by dx. It would be dy by dx. Remember, this is a typical kind of a notation used by Newton and Leibniz. There is a controversy who actually discovered calculus. Some people say Newton, some people say Leibniz, but let us not fight it over. Leibniz discovered calculus from the philosophical point of view. Newton did it from mechanics and mathematical point of view. So this is the slope. So is a infinitesimal small change in the direction of x with infinitesimal small change or an interval in the direction of y. So we are not considering limit right now, because we are considering dy and dx as independent values. Now, for example, we get another case. I will show you case by case so that it is easy for you to understand. We draw a similar kind of a graph, right? And what we get over here is something like this. We get a curve, something like this. Yes, this is the one. And what we are trying to find out is the area under the graph. What we are trying to find out is the area under the graph. So what we do typically is that we are dropping, say for example, perpendiculars. I'm dividing this one into four. Yeah, these are the four lines, right? And this would be, so how we can calculate the area? What I'm going to do is that I'm going to join these infinitesimal small points which we have divided, right? This one and this one and this one, right? And I am going to get the area under the rectangle. These are the areas under the rectangle, and if I sum up all these areas, I'm going to get the area of the graph. Very simple. Now if we are adding up all these areas, right? If you are adding up this one, if I'm adding up this one, and further I'm dropping another, and I'm considering this part, so it will be added, but there is a small error. What is the error? You will see this part, all these parts will have very small areas which are not being covered, right? So these parts are not being covered, which doesn't fit inside the graph. You see this top portion, there's a little bit of error. These things are not fitting in. So what we do now is that we make this delta x, or this change in x from this point to this point, infinitesimally small. We make it so small that this part of the error is removed. So if I draw a very rough graph, let me draw it very rough for you. So this one, and I get a graph like this, and instead of doing bars like this and this, I will take very small thin strip, this one, so that this part, the error which is there, this is removed. So I call it as removed. So I'll just repeat. I'm going to make this typical, this, you can see this small thin strip, so small that this particular error which is not fitting inside the graph is removed, right? So now let me draw a fresh page for you where all these four graphs would fit in, and I will show you in parallel that how it all relates to each other. So what I'll do is that I'll take a fresh page, and just bear with me for a few seconds because I need to draw four graphs which would be lying with each other, and I hope that this camera and everything fits in and you can see them properly. So the first graph, which we draw it from the earlier one, so I draw it like this, and the second one I draw it like this. Okay, I will draw also the third one. So this one and this one, right? So now just let me draw the graphs. So we got the same function over here. So in the first part, what I am doing is, yeah, So this one which has gone up, this is a typical one. Okay, so and the second one is also the same thing, right? So I will first make these things happen. So if this one is happening, then what we do is that, as we have mentioned, this is 1 point, so we are dropping this part so that we can get an interval. We further move up to here and we drop another one so that we get an interval over here. This part we call it as delta y. Okay, this part, let me see, there's a camera is a bit problem. Okay, yeah, this one is the delta y and this one is the change, we call it as delta x. Similarly, we get another graph, and here what is happening is that this part and this part is infinitesimally small, the small change which is happening over here. Now what I will do is that I will quickly mention this one, which is the very small minute change. This part, as we have mentioned it as dx. This small change which we have called is called a dy, right? And let me now put the equations which we have learned. So if we are considering slope as m, in this case it would be m equals to delta y by delta x, that is this change, rise over run, right? This would be x, I'm so sorry, this would be delta x, right? This would be also the same, but in this case, because it is small, we are using dy by dx. Now let us consider these two situations where we got a kind of a curve which is going on. Here we also have got a curve which is going on, right? So and now in this case what I will do, I will just show you with another color. So in this particular case what I am doing is that I am dropping those lines which I have mentioned, 1, 2, 3 and 4. Let us consider these parts. So 1, 2, 3 and 4, right? Now what is happening over here is that, see, I mentioned these 2 points, say for example as A and B, right? From here to here, this is the maximum thing we have taken. So if we want to find this area, say for example this one which I told you, we have divided those, but remember this is something which you're not considering calculus, right? In this type. So we can mention this area, let us call it as A, equals to sigma, okay, because these are finite triangles, finite rectangles. So I can call it as I equals to 1, although there are 4, 1, 2, 3, 4, I consider it as n, that is for n numbers. Area of the rectangle is base times height. What is the base? Base is the function, so we call it f of x. And what is the height? This is the height which has caused the change, which is delta x, right? So this is the small change, right? This part, this is the delta x part. So now you see what we have done over here is that we have used sigma. As you have seen in my previous video, that sigma is used in case of non-continuous functions. So we are considering I from 1 to n, base multiplied by height multiplied by base. Height is the function of x and this is the base is the change, that is the delta x. Now we are going to the final part, which is this one. This we are considering so small thin strips, infinitesimally small thin strips. So it is very difficult to distinguish between one another, although I cannot draw infinitesimally small strips, but say for example, in order to know, so this part which I am doing, this particular triangle, this particular rectangle, so in this case what I can write is that I can use the same thing, A, which is the area, we consider this A, but in case of a sigma I am using the integration sign. Here it is, right? From A to B, right? You can consider this one as A, this one as B, these 2 points, A to B. What is the height? F of x, just similar to this one, f of x multiplied by dx, which is the width, So just let me write it for you. This one is the height, This one is the width. This one is also the height. This one also is the width. So that actually is what we are doing, the differentiation between the sigma sign and the integration sign. So sigma, remember that when we are using sigma, it means that whatever it can be the area of a rectangle, it can be summation, it can be whatever. Whenever we are using sigma, it means that we are considering finite or discrete amounts. See, we just considered this one I to n, height multiplied by width. Height, right? So this is height and this is the width, this part. But whenever we are using this integration sign, right, and using a to b, this is from here to here, that means it has got infinite amount of triangles or rectangles or polygons, whatever. So in order to sum it up all, I can write that sigma, if I use, say for example, I equals to 1 to n, right, this is something which is denoting finite. This is something which is denoting finite. If I use an integral sign, say for example from base a to b, right, this means that it is infinite. Infinite in the sense infinitesimal small areas which are considered. So that brings us to the end of the video. So before I end, I would just like to have a quick recap on whatever the things that we have learned. So we first started with this, what we call is a function. I have demonstrated a very simple example of x5 where whatever the amount of input which is happening here is getting multiplied by 5 and it is the output. In the similar way, you don't have to always use x, you can use a, g, whatever the way you like. So this is basically a demonstration of what is a function. We also showed you how you can use dy and dx in a different algebraic way, and you can find out that this is an operator. So this actually shows the notation, this part, this is the integration sign, these are the two symbols, and the function gets stuck in between these two symbols. We also have learned that the differentiation is inverse of integration. It is something that whatever you got, if you do a square, you get a similar kind of x. So whatever is going in with the differentiation, if you do the integration, it comes out to be the same result. And this is why we have shown that this particular expression shows that if we start with a function, integrate the function and differentiate it, it both remains the same. We showed a simple kind of an example of an antiderivative where you use x4. It is something which is called a radical and a radicand. Whatever you're putting in over radical, and it is the radicand. We also showed you with a similar kind of an example how we can calculate the slope of a graph using the function fx, delta y by delta x. And here we have also shown that if it is an infinitesimal small change, then how you can calculate substituting the delta with dy and dx. Finally, what we have also shown are 4 consecutive graphs. This part shows the change delta y by delta x. This is also the same thing, but it is infinitesimally small, so we use dy by dx. Here, if you want to calculate the graph area under the graph, we use sigma, which denotes that it is finite rectangles we are calculating the area, and whenever we substitute with an integration sign, what we do, we calculate infinite amount of changes, infinite amount of small rectangles which we are unable to show in the physical drawing. So this is the difference. Sigma, whatever the value range 1 to n, is finite, and this is infinite. So that brings to the end to the first part of the video of calculus. This is basically building up the concepts. We would soon come up, I would be showing more videos on integration, calculation, concept building, and the basic fundamental theorem of calculus. I hope you liked it, and if you have any comments, please put it in the comment section. If you want me to make certain videos on certain difficult concepts of calculus or integration, do let me know. I hope you will enjoy this video. Stay happy, stay well, and do stay safe. Thank you very much.